Welcome back to the deep dive. If you've been following tech, especially over the last few years, you've definitely watched this huge shift happen with language models. It's almost tectonic.
Yeah, absolutely. They went from being these very specific little tools, right?
Exactly. Like you'd have one model just for translation, maybe another one just for summarizing text.
And
Yeah.
now we've got these unified, generalist foundation models. They can handle almost any language task you throw at them.
It's a completely different ball game.
And, that whole transformation in NLP, natural language processing, it was based on surprisingly simple ideas, technically speaking.
Simple how?
Well, just training these enormous generative models using web-scale data, mountains of it.
And that gave us zero-shot learning, right? Where you don't need to retrain for every little thing.
Precisely. So the big question we're digging into today is, well, is machine vision, specifically these big generative video models, are they on the exact same track?
Are they about to become the sort of general purpose foundation models, but for vision?
That's the core question.
Okay, so our mission today is really focused on VO3. It's one of these huge generative video models, and there's this incredible analysis we're looking at.
Yeah, the researchers really put it through its paces. They looked at, what, over 18,000 generated videos?
18,384 to be exact, across 62 qualitative tasks and 7 quantitative ones. So this wasn't just like a few cool demos.
No, this was a serious stress test.
Yeah.
And the initial takeaway, it's pretty striking.
Which is?
VO3 can solve this huge range of really complex visual tasks it was never specifically trained on or adapted for.
So purely emergent abilities.
Exactly. Zero shot. And these skills, they span the entire vision stack, everything from basic perception, like just seeing things, all the way up to some quite complex reasoning.
You know, seeing how fast language models evolved, I kind of expected vision to be lagging behind a bit more. In NLP, that generative approach just wiped out the need for all those custom components, that painful fine-tuning.
You just swap the code for a text prompt.
Right.
But that's the disconnect we see now in vision. It still looks a lot like NLP did a few years back.
Meaning lots of specialized tools.
Yeah, really good ones, don't get me wrong. Models like Segment Anything for, well, segmentation, or the YOLO family for object detection. They are masters of their one specific craft.
But ask them to do something different.
Ask Segment Anything to, say, deblur an image and then find the edges. It can't. It fails.
But the architecture, the underlying design of these new video models like VO3, it's basically the same as the language model approach, isn't it?
Exactly the same primitive. Large-scale training, a generative goal like predict next frame or continue the prompt, and just massive amounts of web-scale visual data.
So if that NLP precedent holds true...
And we should be on the verge of a very similar paradigm shift for machine vision. The generalists could start overtaking the specialist pretty quickly.
Okay, let's unpack those emergent zero-shot abilities then. The research broke them down using a kind of hierarchy. 4 levels.
Yeah, 4 levels: perception, modeling, manipulation, and reasoning. And the idea is for really complex stuff, you need all 4 working together.
Give me an example.
Okay, think about solving a maze visually. You need perception, obviously, to see the maze walls.
Right.
Then you need modeling to kind of understand the layout that's stated where you are. Manipulation is needed to actually, move through the path in the simulation.
And reasoning.
Reasoning is to figure out the best path forward, to make the right choices at each junction.
Got it. Okay, let's start at the bottom. Perception. Seeing the world. You're saying VO3 can do standard computer vision tasks, but zero shot.
Yeah, things like edge detection, segmentation, super resolution, even de-blurring and denoising images. All without specific training for those tasks.
Which already suggests these could replace a lot of existing tools.
Potentially, yes. But the really surprising part, for me at least, was how it handles visual ambiguity.
Ambiguity. Like
Yeah.
optical illusions? You mean like that classic Dalmatian picture where the dog's kind of hidden in all the spots?
Exactly that one. It can resolve that ambiguity when you prompt it correctly. But even more fascinating, they tested it on interpreting Rorschach ink blots.
Wait, the psychological test? Seriously?
Yeah. You prompt it, and it generates these plausible, contextual interpretations of what the blot might represent.
Hold on, that feels like a huge leap. Interpreting Rorschach blots isn't just pattern matching, is it? It's about pulling meaning from something really abstract and ambiguous.
Well, that's the implication,
Yeah.
right? The fact that it can interpret images like that suggests it's developed this really rich, internal, latent model, a model of objects, context, even semantic meaning.
All learned just from watching videos and seeing images online.
Apparently so.
Mm.
It's not just finding edges anymore, it seems to be interpreting the scene, which suggests these zero-shot abilities run deep. It's more than just pixel-level stuff.
That's wow. Okay, moving up the hierarchy. Next is modeling. This is about understanding the physical world, like intuitive physics.
This is where it gets really exciting, I think. It's not just making videos that look plausible. It seems to understand cause and effect. Like buoyancy? The model can simulate the difference between how a heavy rock sinks really fast versus how a light plastic bottle cap just floats. It gets rigid body dynamics versus soft bodies.
The one that really jumped out at me from the paper, though, was the gravity simulation. You could prompt it to show an object falling on Earth versus the moon. How does it model the lack of air resistance on the moon? Zero shot. That seems like it needs, I don't know, a physics engine built in.
It doesn't have an explicit physics engine, no.
Yeah.
But think about the sheer volume of data it's seen. Trillions of frames. That data implicitly contains these physical laws.
Just from watching things fall on Earth.
Mostly, but also probably diagrams, animations, maybe even movie clips showing space or physics concepts visually. It learns these abstract visual principles from the data.
And the optics simulation was pretty stunning, too. Reflection versus refraction.
Oh yeah. You ask for a mirror sphere, you get standard reflections of the background, but ask for a glass sphere.
And the image seen through it gets inverted and distorted, just like real refraction.
Exactly. It shows this deep, generative understanding of material properties, how light interacts with different stuff.
And this internal model seems consistent, too. You mentioned world memory.
Right. The research showed if you prompt it to zoom in on part of a scene and then zoom back out, the original scene stays consistent. It remembers what was there. That consistency, that memory, is sort of the bridge to the next level.
Which is manipulation. So if it can see the world perception and understand its rules, modeling, now it can start changing it plausibly.
Yep. And this isn't just about making cool videos. It's about control, about editing the visual world.
So standard editing tasks, like removing backgrounds, changing styles, filling in missing parts.
All those, yes. Zero-shot in painting, style transfer, background removal. But more impressively, it can simulate complex actions, planning sequences of movements.
Like the example with the robot hands.
Yeah, simulating robot hands, opening a tricky jar, or throwing and catching a ball. That requires planning fine motor control over time, based just on a simple text goal like, open the jar.
Or generating visual instructions. I saw the one about rolling a burrito step by step.
Right. It's sequencing actions visually towards a high-level goal using its internal world model.
Which naturally leads us to the top level, reasoning.
Yeah.
And this is where the chain of frames idea comes in, COF.
Yes, COF. The researchers explicitly frame it as the visual equivalent of chain of thought, or COF, which we use for prompting large language models to reason step by step.
Okay, let's make sure we nail this COF concept. Why does generating a video, frame by frame, enable better reasoning for visual tasks compared to, say, a static image model?
Okay, think about it like this. When a language model, say Gemini 2.5 Pro, solves a maze given as text, like ASCII art,
Yeah.
it solves it abstractly. It uses its language processing ability, generating text tokens step by step, turn left, go forward, etc.
Yeah.
But if you give that same powerful LLM the maze as a static image, it tanks. It struggles really hard.
Why? Because it can't see the steps? It can't mentally move through the image?
Pretty much. It loses that ability to reason sequentially within the visual space. It can describe the image, but it can't easily operate on it step by step in its head.
Ah, okay. So COF, chain of frames, changes that how?
Because VO3 is generating a video, it's inherently sequential, frame by frame, across time and space. It's literally performing the visual task incrementally.
So it can visually check its progress at each frame, see if it hit a wall in the maze.
Exactly. It could turn the corner, see the new path, assess the next move, all within the visual medium it's generating. This step-by-step visual generation is what lets it succeed at things like maze solving.
And also visual sequence completion, or even those basic Sudoku puzzles they showed.
Right. And even applied reasoning, like figuring out how to use a tool like a little grabber to get a walnut out of an aquarium.
Yeah.
It understands the required physical interaction.
Now, you mentioned speed earlier. The rate of improvement, that seems crucial here.
Absolutely crucial. Look at the quantitative results comparing VO2 released April 2025 to VO3, which came out just 3 months later, July 2025. The jump is, well, it's huge.
That's incredibly fast development. Okay, let's put numbers on it. The maze solving data.
Okay, so on 5x5 mazes, which
Yeah.
are Genuinely tricky. VO3 got a 78% success rate if you gave it 10 tries. Pass it 10.
Okay, 78%. What was VO2?
VO2, just 3 months earlier, 14%.
What
14%.
about from 14% to 78% in 3 months?
That's the kind of massive, almost discontinuous leap in capability that signals something fundamental is changing. That smells like a foundation model moment.
And it wasn't just beating its predecessor, it showed advantages over other types of models too, right?
Yeah, they compared it to a top image editing model called Nano Banana. That model could handle simple, regular mazes. Okay, probably just pattern matching. But give it an irregular maze, one that breaks this simple pattern. Nano Banana failed completely. VO3, using its co-reasoning, could still solve those. He was actually figuring out the path.
Okay, but we need to be balanced. It's not perfect, right? Where does it still struggle?
Definitely not perfect. The research is clear on that. It still has trouble with really complex motion planning. The example they used was trying to get a big, rigid sofa through a narrow doorway in a video.
Ah, the classic sofa problem.
Exactly. It struggles to maintain the rigid body nature of the sofa consistently while maneuvering it. It might bend it unrealistically.
What else?
And also following precise physics instructions. Like you give it annotations showing specific forces or motions, it doesn't always follow them accurately. Its intuitive physics isn't quite precise engineering physics yet.
That's really important context. Okay, let's talk economics. Because the immediate pushback is always, video generation is expensive right now. Much more than running a specialized model that just does one thing well.
That's true. Today. But we have to look at the history of LLMs here. People made the exact same argument about early GPT models.
And what happened?
Inference costs plummeted. Historically, they've dropped by factors anywhere from 9x to sometimes 900x per year for the same level of performance.
900 times.
It varied, but the trend was drastically downwards. So if vision follows anything like that trajectory, the cost of running a generalist video model could become trivial very quickly. And then that one model for everything approach looks extremely attractive.
Okay, but what about the jack of all trades, master of none argument? You mentioned its edge detection, for instance, is maybe slightly below the specialized state-of-the-art models.
That's a fair critique, and it mirrors the early days GPT-3 too. The defense is twofold. First, look at that improvement rate again, 14% to 78% on mazes in 3 months. The mastery might be coming faster than we think.
And the second part?
The potential for inference time scaling. The data consistently shows that performance is much better if you allow multiple attempts like pass at 10 versus pass at 1.
So you can just run it a few times.
Yeah.
Or have it refine its own output.
Exactly. Generalist models often benefit hugely from techniques like self-refinement or just generating multiple options and picking the best one. That can boost reliability dramatically, potentially closing the gap with specialized models, even if the single-shot performance isn't quite there yet.
This brings us to something really practical, maybe the most actionable takeaway for anyone wanting to use these tools.
Yeah.
Prompting. Control.
Oh, absolutely critical. The research hammered this home. The quality of your prompt, both the text part and any visual input you provide, makes a massive difference.
How massive?
Okay, get this. On a straightforward visual symmetry task, just asking it to make something symmetrical. The difference between the best prompt they tried and the worst prompt, it accounted for a 40 to 64 percentage point swing in the success rate.
40 to 64%, just based on how you ask the question.
Yep, that's huge. It means the difference between the model failing miserably and performing competently can literally just be down to how well you word the instruction.
Okay, so for anyone listening who might eventually integrate these kinds of foundation models, what are the key prompting best practices they need to know right now? Let's say top 3.
Okay, number 1, remove ambiguity. Don't just say, make it symmetrical. That could mean horizontal, vertical, rotational. You need to specify. Make it symmetrical along the central vertical axis. Be precise.
Makes sense. Number 2.
Specify constraints. Tell the model what should not change. VO models seem to have a strong bias towards animating everything in the frame. So if you need a static background or the camera locked off, you must explicitly state that. Static camera, no zoom, no pan.
Okay, be explicit about what stays still. And the third tip was kind of counterintuitive, the motion outlet.
Yeah, this one's clever. Since the model really wants to generate motion, sometimes giving it a small, unimportant place to put that motion can help keep the main part of your scene stable.
How does that work?
So if you need your main subject to be perfectly still, but the model keeps jittering it, you could add something like, add a small spinning color wheel in the bottom right corner. You give it a motion outlet.
Ah, so you channel its desire for movement into something harmless, away from the important stuff.
Exactly. It satisfies the model's prior for animation without messing up your core visual.
Fascinating. Okay, this has been a really deep dive into what looks like the next major chapter for machine vision. The core finding seems incredibly clear.
Yeah, these large generative video models like VO3, they're showing these emergent zero-shot skills right across the board: perception, modeling, manipulation, even reasoning.
Positioning them to become these unified foundation models for vision, just like LLMs did for language.
It certainly looks that way. And it's worth remembering, all the performance numbers we talked about, they're probably a lower bound on what the model can actually do.
Because of the sensitivity to prompting?
Precisely. Better prompting might unlock even higher performance. The confidence is likely higher than the current measured performance suggests.
So the final thought then. If this chain of frames really allows these models to reason visually across space and time, and we're seeing capabilities jump from, 14% to 78% on hard visual puzzles in just months, we really are watching that GPT-3 moment for vision unfold right now.
It feels like it. The pace is astonishing.
So the question to leave everyone with is, what complex step-by-step visual planning tasks become possible next? Forget just generating cool videos. Think planning robot movements in a warehouse, designing complex assembly sequences for manufacturing, maybe even running entire physical processes based on visual input. What happens when these models get even bigger and get fine-tuned for specific applications?
That's the multi-billion-dollar question, isn't it?
It is indeed. We'll have to leave it there for this deep dive. We'll see you next time.